They had planned to introduce a real-time heart rate monitor to get kind of biometric information from the crew directly. There's also additional sensors in the spacesuit that weren't in the old design. You're going at extreme speeds into extreme environments with extreme temperatures and pressures and all that stuff. And those require creative and extreme solutions that push the boundaries of whatever the technology can do at the moment.
Welcome to the Omar Al-Aili podcast, your go-to podcast for exploring the diverse fields driving space exploration and technology. I'm your host, Omar Al-Aili, and today I'm thrilled to be joined by Professor Claas Olthoff, a professor for human spaceflight at the University of Stuttgart here in Germany. Claas is a leading mind in developing the very systems that keep astronauts alive and healthy, from advanced life support in deep space missions to the next generation of spacesuits for the Moon and Mars. Claas, it's great to have you on the podcast. Thank you for making the time.
Hi, Omar. Glad to be here.
As we know, human spaceflight depends on an array of critical systems far beyond power, propulsion, communication, and navigation. Those critical systems must work in concert to keep astronauts and crew both alive and productive. Why is a truly cross-disciplinary approach no longer optional but essential to advance the life-critical systems enabling human spaceflight?
That's a great question. Human spaceflight systems are extremely complex, as you've noted, right? And all the different disciplines kind of work together. And even just in my area of life support systems, there's so many different aspects, right? Because, of course, the life support system needs power. So you need power engineers or electrical engineers. It produces heat. So you need thermal engineers that remove the heat that the humans in this case produce. Then you also need to remove the CO2 that we exhale. So that's usually chemistry that's involved there that absorbs the CO2 or the water vapor from the atmosphere. Sometimes it's physical processes, right? The water is actually usually just condensed out of the air. So that's, physical processes. And then of course you also need to understand the human, all right? Because we're as an integral part of the life support system as the machines are. So you also need biologists and medical doctors. And so, just in my little niche, interdisciplinarity is a must, definitely.
Okay. So a class, usually on a 6-month ISS or International Space Station stint, resupply is your lifeline. But for long duration lunar output missions, or even more for a Mars mission, that lifeline, while it does not disappear, that lifeline, let's say, becomes critically less reliable, which is forcing us to rethink everything. What does planning and designing for extended mission durations, and here we're talking years rather than weeks, what does this extension and mission duration reveal about the shortcomings of today's life support systems?
Well, I have to defend my colleagues working on the International Space Station a little bit. And you said the resupply becomes less reliable. Maybe it becomes more expensive, right? And even just bringing things into low Earth orbit where the ISS is flying around, it's still quite expensive to bring materials and resupply there.
Sorry, I meant will become less reliable when our missions further extend beyond low Earth orbit to Mars or lunar outpost. That's why.
Yeah. But still, the word reliable, that to me, that signifies, it becomes more likely that the supplies don't arrive at their intended destinations for whatever reason. But anyway, even on the ISS, it's expensive to bring stuff up there. So for the life support system, there is already a lot of regeneration happening, right? So the buzzword or the keyword is regenerative life support systems. So we take the things that the human body expels and no longer needs, right? So that's the CO2, the water vapor, but also our urine and our feces. And we try to squeeze everything that we can reuse out of those substances and put them back into the system in the loop. And that's actually something that already is happening on the International Space Station. So we're somewhere between 90 and 95% of the water that is used up there or is produced by the humans is recycled, right? And so that's typical yesterday's coffee becomes tomorrow's coffee thing, that the urine and the water vapor that we exhale and that we sweat, that gets recycled. There's also systems up there that recycle the CO2. So the CO2 gets absorbed, and then through a chemical process, I kind of chop off the carbon atom from that molecule to get your oxygen back.
Mm-hmm.
So those are things that are already being done on the ISS today. And so the expectation is that if we move further away from Earth, that would still happen. The one thing that we can't generate that easily and not with the machines that are available to us is food. There's no chemical or physical process that you can employ to produce your own food.
Mm-hmm.
And for that, we need plants or any other living beings that can turn our other leftovers back into food. So that's something that's being considered for missions that are of longer duration and further away from Earth.
Okay, so what is the most profound system level challenges that emerges when you stretch a mission from 6 months to years for, let's say, a Mars transit or a surface stay?
Well, there's multiple things that happen, right? Because of course you're leaving the vicinity of Earth, right? When you're on the ISS, you can get back home in a matter of hours. If you're going to the moon, depending on your mission architecture, it's the pure flight time is a couple of days. If you're on your way to Mars, there's really no good way back home, right? So, and that's quite a big step. Right, this unavailability of an immediate return capability that produces lots of conditions that you don't want to be in necessarily. So you have to make sure that all your systems are robust enough, redundant enough, that you have enough emergency supplies to hold you over in case something goes wrong. So there's a multitude of things. For the life support system, it's what I just mentioned, the food, right? If you're away for that long, even bringing food with you that's healthy and has enough of the nutrients that we need for several years or even more, that's hard. But also things like radiation, right? When we're flying outside of the Earth's magnetosphere, that becomes a problem that needs to be dealt with.
Mm-hmm.
I think those are the big ones.
Okay. So your new lab at the University of Stuttgart is focusing on the foundational trio of the life support systems, like you just mentioned a minute ago, the CO2 removal, thermal control, and oxygen generation. These systems and their interactions have been challenging us since the days of the Apollo missions. From a systems engineer perspective, what is the most complex and difficult interaction between these three subsystems that designers have to constantly balance, and why?
That's a good question. I don't necessarily know if there's one interaction that's more complex than the other.
Okay.
It's basically the combination. Right. It's usually when you're designing these systems, you design them on a subsystem level. You design them with certain requirements and boundary conditions that you assume. Sometimes they might be variable boundary conditions, right?
Mm-hmm.
So if we take the example of the CO2 removal system during the day when the crew is up and about and active, and in the case of a microgravity mission working out quite a bit, there's lots of CO2 in the atmosphere that needs to be removed. But then at night when everyone's asleep, then it's less, right?
Mm-hmm.
And so the CO2 removal system must be able to provide the removal rate no matter or within the bounds of the expected concentrations. But then, you have other systems that are inside of your habitat or your space station that
Mm-hmm.
might influence the level of CO2, right?
Mm-hmm.
You might have some little spheres flying around your space station that produce CO2. In case of longer term missions, you have plants
Mm-hmm.
or algae that consume CO2.
Mm-hmm.
And these kind of interactions become more complex the more systems you add. And to kind of capture that complexity, that's the kind of the main goal of the work that we're doing here.
Okay. I wonder, on the International Space Station, is there like a 3-astronaut mode for life support, a 6-astronaut mode, like you just press a button and the system changes, or is it everything they have to control from ground control?
I don't know specifically if there's a mode, because again, the life support system and the space station in general is extremely complex.
Mm-hmm.
I know that there's several CO2 removal systems on board the space station that are in some cases for redundancy, but also to actually be able to handle these situations where the crew size increases due to crew handovers. So usually they do it in a way that the new crew that comes up overlaps with the crew that's on their way back to the surface. So they can give them a little bit of on-the-job training on the space station.
Okay.
And then instead of your regular 7, you have, either 10 or 11 people on board.
Mm-hmm.
And then they basically activate the backup systems or the redundant systems to provide the additional CO2 removal capability in this instance. And I think the other parts of the life support system are dimensioned in a way that they can be scaled and capabilities can be added and removed as needed. But I don't know if there's a button that someone presses on the ground that says now there's 10 people. And it's made a little more complicated that, as you're probably aware, the space station used to be, or the plan was to be 2 space stations that got connected in theory in the 90s. So there's the Russian segment and the American segment, and they're somewhat independent of each other.
We're staying now still in general questions about life support systems. We'll go into the details about your actual work in a bit. You also teach about in-situ resource utilization. So how does the introduction of in-situ resource utilization, for instance, extracting oxygen from the Martian atmosphere or from lunar ice, let's say, how does this introduction change the equation and change the trade-offs one have to make between these 3 core functions, let's say?
Yeah, I mean, that's, as I mentioned, right, the resupply is the thing.
Mm-hmm.
And all of the technologies, the physicochemical technologies that we're using today that are available to us, they're not 100% efficient, right? So we can recycle 90, 95, maybe a little more percent of the water, but that still leaves your 5%, right? And getting that from a different source that's not Earth is very helpful, because that means you don't have to bring it with you. So for the moon, right, we're hoping to find water, ice in a form that is usable and processable for us to use for not just breathing, but also drinking. And of course, you can electrolyze it into hydrogen and oxygen for a rocket propellant. And then on Mars, it's similar, right? We're also hoping to find water there in different forms. And since the atmosphere has lots of oxygen in it, but unfortunately bound in carbon dioxide, we can basically use the same chemical processes that we use on the ISS to split up the carbon and oxygen, but just do that with the Martian atmosphere, right? And that helps us to not have to transport lots of oxygen to Mars, which is even more expensive than to the moon and low Earth orbit.
Yeah, I can imagine. Claas, on Earth, we're seeing a massive push for autonomy, like in cars and industrial plants, etc. Now, in space, planning for long-duration missions burdened with both fragile resupply lines because of like radiation, food might get damaged on the transit or stuff like that, and potential communication delays. Autonomy stops being a luxury, right? It becomes a necessity for survival. What level of autonomous decision-making and resilience requirement should a life support system realistically have?
That's active research that you're talking about, right? That's what's the right balance. The ISS, the way it's operated, obviously you have the crew on board the space station, and then you've probably seen images of the control rooms in Houston and Munich and Moscow and Japan. But those are also only just a few people. But in reality, there's hundreds and even thousands of people in the background that you don't necessarily see that help operate the space station every day. And whenever there's something small goes wrong, then there's a whole chain of people behind the astronauts that help them solve problems. And if you're on the moon, right, you have a signal delay of second and a half one way. On Mars, that's goes up to 22 minutes in the worst case.
Yeah.
And so if you say, Houston, we've had a problem, and then you need to wait for 45 minutes to get an answer, if there is an answer that fast, that doesn't work, right? And so you mentioned the word autonomy, right? And there's kind of the one thing is the crew autonomy, right? How autonomous can the crew or must the crew be able to operate? And then there's the autonomy in the sense of autonomous vehicles and systems and those kind of things. And that balance, like what does the habitat or the spacecraft decide on its own? Where does it involve the crew? Which things need to go all the way back to Earth, right? That those decisions, that's basically what's currently being researched all around the world when people are thinking about missions to Mars.
Okay, if I can linger here a bit more, from your opinion, like, should it be able to independently, let's say, shut down a faulty component, reroute resources, and then simply inform the crew and inform the distant mission control of the actions it took?
Yeah, I mean, that's the kind of the human machine interface part of that autonomy. That's going to be key, right? Because astronauts, and I think anyone who's operating some sort of vehicle, or if it's a self-driving car that you're in, you kind of want to know what's happening, right? The car, if a wheel falls off, you kind of want the car to tell you that a wheel just fell off. And so similarly, right, if there's, major actions happening that the system is doing autonomously, then the crew definitely should be informed. For smaller things, right, it can be something like, an email inbox that they check regularly or once or twice a day, where like, oh yeah, the habitat shut down this fan over here because it was getting too hot and it automatically scheduled a repair job for me for tomorrow. That's fine. But I guess depending on the criticality and severity of the action that the system takes, should alert the crew faster if required.
Okay, but how do you build trust, both for the crew and the mission controllers, in a system that literally holds the crew's life in their hands?
Yeah, I guess test, and then test some more. That's the key. Obviously, it's really complicated, right? Because it's already super expensive to do these things, and then to say, well, we're going to build a whole kind of duplicate system on the Earth and then operate that for months or years on end and try and find out where these where the problems are, right, and remove most of them. And that's actually one of the things that we're working on here. So we're developing together with others a life support system simulation tool where we can basically run many different scenarios in a computer without involving people, and especially people's time, because that's actually what's most expensive about spaceflight projects, right? It's not the hardware, but it's the salaries of all the engineers that have to work on it. And it's something that takes some time. Anyone can build a simulation or a model of anything, but to build that trust over time, that's going to be necessary for all the parties involved, and especially the safety and mission assurance community to trust those results.
Yeah, that's a great answer. That's also a segue to, we're moving now to the simulated environment part. Your more recent work is heavily reliant on advanced simulations. In the broader tech world, there's sometimes skepticism about simulations. For the entrepreneurs, engineers, and scientists in my audience who might be considering developing their own simulation environments, what is the argument, or what can you make the argument for why high-fidelity simulation is not just a cost-saving measure, but an indispensable tool for discovery?
Yeah, I mean, as I mentioned, right, the just looking at the life support system, right, because that's my main area of expertise, but it applies to the whole system. They're very complicated, right? And there's so many different moving parts and so many aspects that you can't test them all. Right? There's so many different scenarios and so many different variables. If you actually wanted to go and make sure that your system is safe enough, I mean, well, I have to kind of take a step back. All of this is going to come down to risk and the level of risk that we as a species, or whatever, as the operators of space programs, are willing to accept when we do these type of missions. And for when you're doing risk analysis, then there's always kind of the trade-off between, you can't make your system 100% safe, right? That's not possible. Obviously, you're not going to fly a system that will definitely lead to loss of life, but there's a spectrum in between, right, where it becomes more and more likely that bad things happen. And in the end, it's maths and statistics that kind of fix a point along the spectrum where we say, okay, this is where we are, right, in terms of risk, and then it's a higher up decision which what the level of risk is that we're willing to accept. And modeling and simulation, but of course also hardware testing, ideally with humans in the loop, those are all methods that can reduce the risk. Because if you're more confident in your assessment, right, that reduces the risk of what you're doing.
Yeah, what did they say? Don't make it fail safe, make it safe fail.
Safe to fail. Yeah.
Yeah. Okay.
Right. I mean, that's one of the strategies, right?
Mm-hmm.
One of the strategies of making systems as safe as possible / reasonable.
Mm-hmm.
Is to have these kind of redundancies in there that you say, all right, we have 2 or 3 CO2 removal systems and we're good with one.
Mm-hmm.
So one can fail and we're still one fault tolerant while we repair the third one. That's one of the strategies.
Okay, so let's talk about the virtual habitat platform you have been developing. The architecture of this virtual habitat platform is rooted in project-oriented programming, right? Providing a modular structure that enhances flexibility and scalability. It is comprised of distinct environmental sensitive dynamic models and an infrastructure module. Now we'll get to the infrastructure module and validation later down the road. But to start, in your own words, what is the virtual hub? What can it tell us about what can you tell us about the use of dynamic modeling in virtual habitat, and what are the key aspects of its dynamic modeling capabilities?
Yeah. So kind of to give a longer answer, the origin of VHAB is rooted in a master's thesis that was written at the University of Colorado in Boulder.
Okay.
And this person was also a professor in Aachen.
Mm-hmm.
He basically designed a cool life support system for Mars with lots of plants and algae in there to be, cool and fancy and bioregenerative. And then when he presented the results of his design work, someone asked him, so is this system stable? Because when you're dealing with humans, right, we have, our variable inputs and outputs throughout the day. But then for plants, especially, right, they have way longer timescales. So talking about months between, when you grow them until, they start contributing to the gas exchange, until they provide fruit that you can actually consume.
Mm-hmm.
And so the plants also have, inputs and outputs, and they require nutrients and all that, and making sure that all of the mass flows kind of, even out in the end, right? That you don't have a buildup of CO2 somewhere, or it drains the nutrient tanks too fast, right? You need to kind of look at that. And he thought, well, there must be some tool out there that I can analyze this with. And so he went back home and did some research and couldn't find one. And then that turned out to be his PhD topic, right? And so the idea is that you have not models that are steady state, right? That's kind of the opposite of being dynamic, right? So steady state models where you have a component that just filters out a certain mass flow per second all the time, all day, every day. But you have things that are operated in bash mode that get turned on for a while and then off. Where you have a dynamic human that provides these time dependent inputs and outputs. And that's basically the whole idea behind VHAB, right? And the way we set it up is that all of the individual models are objects, right? In terms of, computer science terms, right? Object-oriented programming. So all of the models are, do you need to start over with the phone ringing or?
No, that's fine.
All right. Let's see, where was I?
All models.
Yeah, all of the models are objects, right? So in computer science terms, object-oriented programming, objects. And the way we set up VHAB is that each of these objects has its own time step. So that's kind of our unique selling point, because I haven't seen that done anywhere else in simulation systems of this type. Because usually there's one global time step where you do the calculations every second or every minute or every hour. But in VHAB, every object has its own time step. And
you're talking about time varying interactions.
Well, interaction too, right? So it's trying to explain it without getting too deep down into the weeds of how the simulation system is designed. But basically, so when I say everything's an object, right? So you have, for instance, you have a body of matter, right? So say a tank, right? And so inside of the tank, you have a liquid of sorts, and then gas on the top, right? And if you decrease the liquid level, then the gas volume increases, right? And then the substance has properties, right? Physical properties, right? It has a pressure, it has a temperature, it has a composition, and all those things change over time, right? If I add stuff, then heat capacity increases. And if I add warm fluid, then the temperature of the overall fluid increases.
Okay.
And what happens is that each of these bodies of matter is an object, right? And it can sense how much it's changing, right? Is my temperature changing? Is my pressure changing? My composition, etc. And if that rate of change is high, then it decreases its time step and does calculations of its own internal properties lots of times. But if nothing happens, right? It's if it's your emergency oxygen tank that's just sitting there for months, you don't need to calculate the pressure in there every second. That doesn't make sense. And so the object then itself decides, well, hey, nothing's happening here. I'm going to increase my time step.
Okay.
Right. And with this type of system, we can simulate things that happen very fast and at the same, or not at the same time, but also simulate things that take very long. Right. So my doctoral research was on spacesuits. Right. So you have one person in, 1.0 something square cubic meters of volume for 8 hours. But with the same basic simulation system, you can also simulate a Martian habitat with hundreds of cubic meters and tens of people. Right.
Okay.
The different scales are possible.
But you also have dynamic representations for the crew, right? There's the crew module.
Yes,
within
exactly.
it. Yeah. So how does this interact? Is it the same approach is it just the surface of how deep into identifying, because the human being, if you're representing a human being in such a simulation, that means there's an output. There's carbon dioxide output, oxygen intake, body temperature. Are those also included in the model?
Yes.
Okay.
So the human model is an integral part of VHAB, right?
Okay.
It's the heart of the life support system. And so we have different fidelity human models, right? So we have very simple ones that just are somewhat static, right? They have a fixed flow rate of oxygen that goes in and CO2 that comes out and water vapor and heat. And then you can just have a kind of a lookup table to change that over time. But there's also more complex models, right, where we actually have a thermal layer where the different parts of the human body are modeled, right? The skin, the different fat layers, the muscle layers, and then all the way down to the bone, right, to see how the blood is transported, and then the heat, right? That's something that I needed for my spacesuit modeling because it's way closer to the human body than if you're in a giant volume. There's different levels of fidelity of the respiration model where you can actually simulate the breath pattern of a human in terms of the flow rate. It depends on what you're trying to do with the model, right? Of course, if you're simulating, 6 years on Mars, then it doesn't make sense to go to the detail of, individual people breathing patterns. But if you're in a spacesuit and you're looking at things like CO2 washout, right? If you're exhaling CO2 and how fast does that get drained from the suit, then you actually do need these type of more detailed models.
So I'm assuming you're also working within a microgravity, fluid dynamics physics. So when you're doing those medical issues that astronauts are facing, which can cause fatigue, as the CO2 bubbles that are formed in front of the face, does it also show that? Does it demonstrate that or not yet?
Yeah, well, not directly.
Okay.
It's kind of as the origin of VHAB was more, habitat scale life support systems. We weren't paying that much attention to these kind of very small details of fluid flow. For the spacesuit model, what I did was that I had a separate CFD simulation that was done on the spacesuit to kind of get an idea of the flow rates that the life support system produces, right? So in the spacesuit, the fresh air is blown into the helmet through connector at the back of the head. So you have the airflow in front of the face with the fresh, clean CO2-free air. And then it's removed from the suit at the extremities. So it goes down the arms and the legs and then returns back into the life support system. And so we modeled that in CFD and did a fairly detailed CFD model on that. But then I just used the flow rates that CFD model produced and plugged that into the VHAB model. So it's informed by CFD, but it doesn't do CFD in line with the actual simulation.
So how has the VHAB demonstrated its value in uncovering design flaws or system interactions that traditional analysis would have missed?
Well, I wish I had a good example where we actually found something that other tools had missed. Unfortunately, I don't have that nice of a poster example yet. Hopefully that'll come in the future. But it's both VHAB and then also my kind of specialized version for spacesuits. They've both been used at NASA, where we basically answered some additional questions, right? So it's all kind of what I was referring to earlier, right? Risk reduction, right? NASA, of course, they have their own tools. They have commercial tools that they use to do all sorts of simulations. And then ours was just kind of another one that could answer some questions differently. Right. So we did some simulations of the International Space Station's life support system. We did simulations of the Orion life support system, and kind of what I'm freshest in my memory, at least, is of course the work I did there while I was a postdoc at Johnson Space Center, where a part of the spacesuit simulation was a thermal model of the lunar surface and the spacesuit. And one of the things that NASA's internal tools could not do was the dynamic thermal interaction between the spacesuit and the lunar surface.
Okay.
Right. So you had basically a model of the spacesuit with the human inside at the lunar South Pole, then walking into one of these permanently shadowed craters. And then the objective was to see how the warm suit, right, which then radiates infrared radiation, how that interacts with the cold lunar surface inside of these craters. And that did provide some insight that NASA otherwise wouldn't have had.
Okay, so Claas, the VHAB also includes an infrastructure module that acts as a master controller, monitoring like mass conservation and managing the simulations timeline.
Yeah.
This sounds like the glue that holds the whole platform together. Can you outline how VHAB's infrastructure module ensures that these complex dynamic models, from human physiology to chemical reactors, all interact in a way that is not only stable but physically coherent?
Yeah. So basically, it's we try and encompass three, I guess, domains, you would call them, right? So we have the matter domain, and we have the thermal domain, and we have the electrical domain, right? Those are the three ones that we cover with VHAB. And they all share kind of a very foundational architecture together, right? So again, going back to the object-oriented programming, they all have the same base group of classes, right, that we use to instantiate the specialized objects from, and then through inheritance they get specialized. And on the very lowest level, each of these objects that deal with either energy, be it electrical or thermal or mass or matter, they all kind of report back to a central entity that at the beginning of a simulation kind of takes stock of all the energy and all the mass that's in the system, right? And then over the course of a simulation, I mean, it's a computer, right? It's not a continuous solving system, but it's discrete, so it does do small rounding errors here and there. So it's never zero at the end, right? There's always 10 to the minus something small variations. But basically, there's a central instance that keeps track of all the masses that are in the system, and all the energy. And in the end, it just basically does a comparison between the start state and the finished state. And if the discrepancy is too large, then it gives an alert and says that something's off and something's wrong. At first, when we were starting out and developing the simulation system, that happened. But I think as of a couple of years ago, we've gotten pretty good at knowing where these things might happen. There's also a bit of a separation between the core of the simulation system and what a user would interface with. A lot of these foundational classes that govern how mass and energy move back and forth between the different parts of a model, those are all things that the user shouldn't be changing, right? And that we've tested and where we've built in safeguards and all sorts of checks to make sure that mass and energy isn't created or destroyed without the user knowing.
Yeah. Actually, the VHAB is actually a digital twin for a physically constructed new life support system laboratory for the purpose of validation, right? Right in Stuttgart.
That's the plan.
Yeah. So it's under construction now or still in planning?
Yes, exactly. Yeah. I mean, it's as usual in space, things took longer than I expected. But yeah, no, we're in the process of designing our own little life support system here in hardware. One of the reasons that I want to do this with the seed funding that I'm given by the university is that when you're building all of these models, right, at some point someone's going to ask the question, well, is this model correct? And does it really do or represent reality correctly? And then you need to find an actual system, model it, simulate it, and then have some data to compare it with to make sure that, if it says 5 kilograms per hour of CO2, that's actually the real number.
Okay.
And getting this validation data is really hard if you don't have your own hardware, because then we need to go to industry or to any space agency and ask them for those data. They might not have them. They might not want to give them to us for export control or IP stuff. So that's kind of what we're looking forward to having our own hardware in-house so we can validate our own models directly without having to wait or go through export control. And then, digital twin is, of course, the buzzword du jour for these types of things. I think if that word or that buzzword had been around 10 years ago, we already would have called VHAB a digital twin for the systems that we model. Kind of one of the traits of a digital twin, if you look up the actual, hardcore definition of it, is that it's a system that has interaction with its physical twin. Right. So you have the digital and the physical twin. That's actually something that we've never actually done, that VHAB has always been capable of doing, but we never had kind of that use case. But that's what we're building here. Right. So we have the actual hardware and the simulation model running in parallel, and then having this exchange of information that the sensors update the state of the model, and then the model can also command and control the hardware and make these autonomous system decisions that we talked about earlier.
Okay, so how does this digital twin that's actively learning from a physical system or interacting together in parallel provide insights that you couldn't get from either simulation or physical tests alone?
Well, I mean, simulations are nice because you can basically stick a sensor anywhere you want. And then the physical twin, right, that's kind of limited, right? Limited in the amount of or number of sensors that you can put anywhere. Maybe sometimes the diameter of your piping is just too small for something, or you have to do lots of extra effort to do all the data acquisition and processing. That's actually something that we're looking to do research in, specifically for digital twins. How many sensors are enough sensors, and how few can you get away with, basically, and still have a high fidelity digital twin of your physical system.
That was actually my question: how to avoid the trap of making a model so complex that it becomes computationally impossible, or too simple. It's not used for anymore.
Yeah, exactly. That's exactly the type of research that we're looking to do here once we have all the hardware in place.
Okay, so what's your team's most promising early results in letting an algorithm predict and head off, let's say, a thermal or a flow control anomaly?
So directly with VHAB, we haven't actually done this type of predictive modeling. So one person on my team, he's working in a project where we're looking at AI applications in life support systems specifically. And of course, anomaly detection is also one of the main kind of use cases for AI in general. And we're trying to see how we can apply these principles to the control and monitoring of life support systems. So far, and that's kind of the bridge over to VHAB, right? We're using VHAB to model the life support system of the space station, specifically the Columbus module's life support system. And then we're hoping to get some data from the German Aerospace Center that operates the Columbus module for ESA, to do some training of our AI algorithms, and then do some anomaly detection there. And we're still in the early stages there, where we're trying to identify actually which types of AI algorithms are the most suitable for the applications that we want to use them for. It's again, I'm still getting started, so no early results to discuss just yet.
No, but it's exciting, the work that you're doing. That's why I'm highlighting those things. In your opinion, where do you see machine learning and digital twin concepts having the biggest impact on life support system autonomy in the next decades or so?
Yeah, I think both the detection of anomalies. I think when I've been talking to some flight controllers that work on the life support system,
Mm-hmm.
they are inundated with data that's coming down from the system, hundreds and hundreds of temperature sensors, pressure sensors, flow sensors, you name it, right? Binary things that are on and off, and each of these sensors is, one little squiggly line on their 8 or 10 computer screens that's in front of them, right? And mostly the detection of any kind of adverse situation happens when a value crosses a certain threshold, right? And those are kind of predetermined, from expert input from the people who actually built the hardware that say, hey, if this temperature goes above 23 degrees, then you need to kind of make sure things are wrong. But hopefully what these, machine learning algorithms will be able to do is that they'll alert us earlier, right? So because once it's above 23 degrees, that's when the alert is triggered, but the actual fault has happened way earlier. And maybe there's even some signs of an imminent fault that hasn't even happened yet that can be identified by these algorithms in the data. And so those are the kind of things that we're hoping to do with the research.
You recently spent time at Airbus working on the life support system for the Starlab commercial space station. For our audience, Starlab is Europe's new commercial space station. Hopefully, it'll be done without any setbacks. The Starlab will rely on our next generation life support systems, which you help also shape. What lessons from VHAB and the International Space Station heritage did you incorporate in Starlab's LSS design, and where did you push for radical departures?
Well, I'm not at liberty to discuss any details, right? Because they're kind of
I respect that.
Company confidential things here. But I think that's not just true for Starlab, but that's true for all of the commercial space stations that are currently under development. The timelines that are involved are very short.
Okay.
Right. And the things that are planned for these commercial space stations are not radically different from what's being done on the ISS today or on the Chinese space station for that matter.
Mm-hmm.
So just purely due to the kind of requirements that the proposed missions have and the timelines involved, there's not enough time to do any radical redesigns or push for the use of currently low technology readiness level systems to be developed to a point where they can be safely and reliably used on a commercial space station, right?
Mm-hmm.
Which, in contrast to the ISS, which, is, a science-driven laboratory, right, and to some degree experimental, right? That's way different, right? You'll have paying customers that want to use your infrastructure, and then you say, "Oh, our novel whatever CO2 removal system or water processor that doesn't actually work the way we thought it would. That's not possible. That's not viable, right?"
Yeah.
So, from what I've seen that's been publicly available on the life support systems of these space stations, it's the amount of overlap between those systems and what's been employed on the ISS is fairly large. I mean, they're all kind of the version 2.0 or 3.0 of what's being used on the space station, right? So the lessons learned and the operational experience that's been gained on the ISS over the last 25 or 27 years, that's definitely included. But I don't think there's going to be any radical new technologies employed.
Well, funny you mentioned China a minute ago. On a geopolitical front, China's Lunar Palace has demonstrated closed-loop systems for habitats. Meanwhile, Western programs seem to lag behind, for lack of a better word, because I know that the NASA has stopped bioregenerative design life support systems back in 2004. How do you explain the apparent gap between the Chinese demonstration projects and the Western efforts on closed-loop life support systems? And is this healthy competition or a missed collaboration opportunity?
Well, many questions. So I don't think NASA completely stopped doing bioregenerative life support in 2004. I think there's been some activities there. The first thing that pops into my head is the advanced plant habitat that's run out of Kennedy Space Center, where they're looking at growing plants in microgravity. So it, might not necessarily.
I was saying in a sense of a closed loop system,
right? I mean, so I think the consensus is that bioregenerative life support systems are a necessary solution, but only for very long duration missions, right? The upfront mass that is required to bring up a system that has enough growth area and algae reactor mass and volume to substantially contribute to the atmosphere revitalization and or food production for the crew. That upfront mass is so high that it doesn't make sense to develop these systems to a flight-ready level for short missions, right? And it depends on who you talk to, right? The bioregenerative community will be very optimistic when the break-even point is, and the physicochemical folks will push it back out. But
okay,
we're talking several years at least. If you get more pessimistic, we're actually talking decades until it really makes sense to incorporate plants and algae into a life support system of that scale.
Wow.
The short-term Western goals, right, have been focused on getting to the moon quickly. I mean, they say they want to do it sustainably, but of course, with the kind of frequent changes in the United States and usually associated with a change in direction, the consistency there hasn't really been helpful, or inconsistency better. China has the situation that they can set goals and just keep at them for many, many years. And that's, what they've done with their entire human spaceflight program and life support systems as well. In terms of collaboration, as a scientists, right, we tend to focus on the science and not as much on the politics.
Of course.
In terms of that, collaboration is always better. Either share the load or do more together. When you're doing things collaboratively rather than competitively. But of course, with China, it's complicated. There's lots of different other factors involved that are outside of the scientific domain. So it's hard to say.
Okay. We live in Europe, and Europe and ESA has a different working relationship with the Chinese space agency than the US. In the terms of just pure research and data, has the Beijing Lunar Palace data influenced your thinking or spurred changes to the VHAB assumptions?
Not directly. I have to admit that we haven't actually incorporated a lot of their results into VHAB models.
Okay.
The short answer is no.
Okay.
But it's definitely something worth looking at. I mean, as I said, right, data is always the kind of the life elixir of anyone who does simulations, and the more data the better, right? Because there's always something that doesn't match up, right? When you have a new data set and your existing model, and you try and recreate it and it doesn't work. And then that's how you learn and how you improve your models to make sure that they're as good as possible.
Okay. So this vision of a highly reliable closed loop system feels like the holy grail of life support systems. What are some of the biggest scientific or engineering problems we still need to solve to make that vision a reality, in your opinion?
That's a good question.
Is it a material problem? Is it a chemistry problem? Is it a systems integration? And systems here are not just talking technology systems, biological systems, sensory problems. What if you want to think about something? What would it be?
Yeah, I mean, the reason I'm a little hesitant is that I can't really think of one big showstopper. There's lots of small ones, right? There's things that are problems that are out there that need solving. But none of them seem insurmountable at this point, right? They're all, there's a bunch of little problems. Some are maybe a little bit bigger, but we have no idea how to do this, right?
Okay.
In my opinion, if we wanted to, we could, start a mission to Mars today, right?
start planning,
start developing
developing
it, right? It's a matter of technology development and making sure we have the right materials and processes in place to do things. But I don't think there's any fundamental thing that's missing, right? Except for money. That's, I guess, the problem everywhere. But I'm stealing this from an astronaut whose name I've forgotten, right? Who said, I always get asked how many years is the crewed mission to Mars away, and he says it's not a question of years; it's a question of dollars, right? We're $500 billion away from a human mission to Mars.
Okay.
So that's the answer.
Okay, let's shift gears now to next generation spacesuits and EVA operations. Your PhD, like you said, and a significant portion of your research focuses on extravehicular activities, on EVAs. In essence, you've gone from designing the life support for a habitat to shrinking it down to fit an astronaut's backpack.
Mm-hmm.
What was the intellectual driver for that shift in focus?
Well, so I joined the VHAB team right when I started my PhD, and I didn't have a clear kind of direction of where to go. I knew I wanted to do something with human spaceflight and life support systems, and that kind of was the starting point. And then the Markus Czupala, the professor in Aachen who invented VHAB, he was kind of my kind of unofficial PhD advisor, and he kind of nudged me into the direction of spacesuits and said, "This is super interesting. It's a much kind of more challenging simulation task, right? Because you have these very small volumes, right? And if you have small volumes and small kind of balls of matter, things happen quicker and faster, and you need a higher fidelity of the model. It also required the integration of that thermal simulation system that I mentioned earlier. That was also done by another PhD student who was there with me at the same time. And I basically combined the two
thermos,
tools.
right?
Thermos, yes, exactly. Yeah, the thermal moon simulator. And so I kind of combined the two tools and then added some spacesuit specific models and processes into the mix to generate what I call vSuit, right? So in like VHAB, but just for spacesuits, because it includes this thermal simulation system. Yeah, and so that just kind of flowed naturally from that starting point.
Okay, so beyond the engineering, EVA represents the pinnacle of human exploration. What does enabling that moment mean to you on a personal level?
No, I mean, when I was at NASA, I tried to become a suited test subject, but they wouldn't let me because I was not a U.S. citizen.
Okay.
It's a very sad day. No, I mean, when I was at NASA, I was embedded in the team that built the new spacesuit. That at that point was going to be a NASA product. So I worked on the life support system and had a teeny tiny part in developing that system. And I don't know, that's just amazing to think that at some point, there's going to be a person walking on the moon, and I helped just a little tiny bit. Yeah, I mean that's a dream come true. My dad took me to Kennedy Space Center when I was 5 years old, and that was kind of my initial moment of wow, people are flying in space. How cool is that?
Okay.
And ever since then, I knew something with human spaceflight is what I wanted to do with my career and with my life. So yeah, being just a teeny tiny part of that is 5-year-old Claas's dream.
True. The basic concept for a spacesuit is a personal, pressurized spacecraft, and has been around since the 1960s. The suits used on the International Space Station today are a direct descendant of the Apollo and the Space Shuttle era. From a high level, what are the fundamental classes of spacesuits? And second, despite decades of development, what are some stubborn challenges that has proven the most difficult to solve?
Yeah, so I guess, when you say the word spacesuit, right, most people think of this type of spacesuit, right, the big Michelin man puffy suit. But there's some other suits that are worn inside of spacecraft, right? So there's also kind of the other class of spacesuits that they go by different names: launch and escape suits, launch and entry suits. Basically, the idea is those are suits that you wear to protect yourself in case something goes wrong, right? So they're usually worn during all of the dynamic phases of flight. So launch, landing, docking, re-entry, of course. So in case the spacecraft cabin loses its pressure, then you're protected. But again, those are built for emergencies. It's a suit that you don't really want to use. And then the white spacesuits, right, the actual extravehicular activity spacesuits, those are built to be used, right? You're going into a vacuum, into space on purpose, and you're not going out there for a few minutes, but you want to go out there and work for several hours. And that means the suits are built very differently. And in terms of the pressure garment, right? So if the spacesuit is made up of the pressure garment, the kind of the human shaped part, the life support system, which is usually worn on the back of the suit, and the kind of power and avionics part that's intermingled between the three. And so for the pressure garment, being able to move in this kind of inflated balloon, that's the big issue, right? And that's where a lot of the engineering goes into, is trying to make a human-shaped spacecraft that a human can actually move around in somewhat comfortably for several hours without too high of a level of fatigue, right? But also without injuring oneself. For the life support system, it's always the kind of the mass challenge, right? These things are fairly heavy. For spacesuits that you use in microgravity, it's a little bit less stringent, right? Because you only have to overcome the inertia when you're moving around about the space station. But if you're on the lunar surface, and especially if you're on the Martian surface, the current spacesuits that are used on the space station are way too heavy to move around and to use. So you really need to make sure that you get your mass down and still provide all of the functionality that a life support system needs to keep the human alive.
Okay, so the Artemis program, or the Artemis missions, hopefully will allow us to return to the moon. How does designing a suit for walking, kneeling, and working on a dusty, abrasive planetary surface like our moon different from designing one for floating in the microgravity of low Earth orbit, let's say?
Yeah. So it's basically two things. So you already mentioned the dust, right? So the lunar regolith is very abrasive. In addition to that, partly it can carry an electrostatic charge, which means even if it doesn't get stuck to your clothes or your spacesuit because of the mechanics, is electromagnetically attached to your spacesuit. And of course, in the low gravity of the moon, you can kick up nice high plumes of dust with whatever you do when you're walking around the surface. And it's, if you compare it to sand or dirt on Earth, right, it's way, way finer. So it's more comparable to ash than it is to sand. So it's really nasty stuff, and it gets everywhere, and especially into your seals and bearings. And so that's kind of one of the main challenges for designing hardware for the lunar surface, is trying to prevent dust entry, and if there is dust entry, that your systems are at least somewhat tolerant of dust. The other thing, right, is just the mobility. The spacesuit that's currently used on the ISS, the legs are very stiff because you don't really need them. I think at some point they were considering, when they were designing that suit, to just have no legs at all, but just have sort of a kind of a sleeping bag or sleeve with the legs floating freely in it. Because you're just floating around and you walk with your hands. So, but yeah, having a lower torso that's flexible enough that you can walk comfortably for fairly long distances, that you can kneel down to pick up samples with, that's a big challenge. That's something that the teams at NASA and now the commercial companies are spending lots of time on to make sure that can be safely and comfortably done.
Looking forward, do you see the future of spacesuits as a slow, iterative evolution of current designs, or is there a disruptive technology on the horizon that could represent a complete revolution?
Yeah, so even back in the 60s, when they were thinking about how to protect astronauts on the lunar surface, there was one concept that gained some traction that's called a mechanical counterpressure spacesuit. So everything that's been flown so far are gas counterpressure spacesuits, right? Where you basically do the same thing for the human body that we have here on Earth, right? We have a gas that surrounds us that provides pressure, right? But pressure is just force per area, right? And force can be applied not just with gas molecules impinging on your skin, but you could also imagine having just a very tight garment that you're wearing, right? Where you have, your flexible fabric that's tight enough for your body. And it's, the nice thing is that the pressure that our skin or our body requires is actually quite a bit lower than the pressure that we require for breathing, right? Because that's the other important function that the spacesuit needs to provide, right? A breathable atmosphere. So actually having something that applies this pressure on a smooth and nice geometric surface is actually not that hard. And there have been prototypes that have been used, but our bodies aren't cylinders or spheres or some, kind of easy geometric shape, but they're actually quite complicated. And building a spacesuit that applies this pressure evenly and continuously, even while you're moving, and to all or at least most parts of your body, that's really hard. And so the concept was abandoned then, I think, in the 60s, when kind of it became clear that with the currently available technology at the time, they couldn't realize that concept. So they went to gas counterpressure suits. It was revived again in the early aughts at MIT. There's a Professor Dava Newman spearheaded that development with some NASA funding to kind of advance the technology further, but also they made some progress, of course, with 30, 40 years of technology development, but we're still not there yet. There's been some experimentation at NASA regarding gloves. So I think there was actually a mechanical counterpressure glove that's been flown. The fingers and hands are very complicated geometrically and with all the movement mechanics. But yeah, we're not there yet. But that's kind of the technology that I see in the future that could supplant gas counterpressure suits.
Amazing. Yeah, cool. Claas, the current extravehicular mobility unit used on the International Space Station is a workhorse, but it's also aging technology with known limitations in terms of sizing, mobility, and maintenance. If you had to identify the single greatest operational constraint that the current EMU places on astronauts and mission planners, what would it be?
That's a good question. I actually don't know of any single one off the top of my head. I mean, it's an old suit. It's an old design. There's some things inside of the life support system that are fairly complicated. So there's a component in there called the fan pump separator, right? Which, as the name implies, is actually three components in one, right? Because it's the water pump and the air circulation fan and the separator for condensate. And it's all in one component with one motor that rotates at one set of or one fixed speed. And that's actually a thing that they changed in the new suit design for Artemis, right? Where they basically separated those three components from each other. And now there's separate fans and separate pumps and a separate water separator. So it's not necessarily an operational constraint, but it does make the suit a little complicated, especially when it comes to repairs. And that's actually a requirement that was imposed on the new suit for the Artemis missions, is that it be, well, first of all, it has to be capable of supporting way more EVAs than the old suit, right? Because that was designed for space shuttle missions where they did a maximum of 5 EVAs per mission. Then the suits were brought back down and could be serviced on the ground. For the ISS, I think they upped it to 25 EVAs. So we're, before they get back down to the ground to be refurbished. And I think the requirement for Artemis was north of 100. So a lot higher. And also there's requirements for the maintenance of the suit, right? If, that you have kind of more modular construction with interchangeable components. So you can, if one thing breaks, you don't have to take everything apart, but you can just, remove a couple of screws and maybe a connector, swap a component out, and then you're good to go. So yeah, I think, that's kind of the general direction to windingly answer your question. The requirements are different, right? I think for, microgravity EVAs, the EMU that's currently being used is perfectly fine. I'm sure there's lots of different small things that can be improved and made better, but I think it served the ISS program very well. But the requirements for the moon are just plain so different that we need a new suit.
Okay, speaking about the Artemis program suit, we're now seeing a diversification in suit development with NASA's XEMU, that one that you mentioned you took a little bit part of, where the commercial Axiom spacesuit is derived from, and the SpaceX is developing their own EVA suits. This is a new paradigm in space. What are the benefits and potential risks of having multiple potentially non-interoperable spacesuit platforms developed by different entities, commercial entities, as opposed to the single standardized approach of the past?
Well, I mean, I would argue that it actually hasn't been that centralized in the past, because on the ISS you had American suits and Russian suits, and the US airlock on the space station was actually configured at the beginning to host both American spacesuits and Russian spacesuits. So they had, at some point, they defined an interface between the two. So if the Russian airlock broke for some reason, and at the same time the American spacesuits were inoperable, that you could go outside using the Russian spacesuits in the American airlock.
Okay.
And I don't know for a fact, but my assumption would be that if there are multiple providers of spacesuits in the future, then there will be some sort of common interface somewhere where both suits can attach to the vehicle systems and, get recharged and all that. On a smaller scale, if I remember correctly, there's also, for all of the Artemis hardware, there's a common toolkit requirement where you have kind of a fixed set of tools that you can assume are available on whatever spacecraft we're going to the moon with, and that your system that you're designing needs to be able to be repaired using just those tools, right? So I don't know. I think having multiple providers is in a way good because it provides dissimilar redundancy, right?
Okay.
And I think that's the same approach that NASA has pursued with the Commercial Crew Program and the Commercial Cargo Program, where they had multiple companies and then at the end selected two to provide the same type of service. And well, unfortunately, Boeing Starliner doesn't meet the requirements just yet.
Mm-hmm.
And in the meantime, they have SpaceX Dragon, who's flying reliably to and from the space station and kind of picking up the slack. And I think that's the same type of approach that NASA is doing with spacesuits as well.
Okay, so as we look to augment astronauts' EVA capabilities, what do you see as the next frontier in suit enhancement? So are we going to see more biometric sensors doing real-time health? Are we going to have integrated robotics to enhance strength and dexterity? Are we going to be integrating, let's say, assistant or medical AI? That kind of things.
I would say yes to all of the above. So some of the things, so with sensors, right? I think for the new, so I always have to be careful. So I worked on the XEMU, right? Which is currently, they have designated as the NASA reference design. That the commercial companies that won the contracts can work off of. And so for the XEMU, they had planned to introduce a real-time heart rate monitor to get kind of biometric information from the crew directly. There's also additional sensors in the spacesuit that weren't in the old design. So you have some more monitoring of kind of the health of the crew indirectly by monitoring the temperatures and gas composition and those kind of things. The XEMU incorporated a modular informatics system that was separate from the actual kind of the suit operational hardware, but something that is there for displaying information to the crew. There's a head-up display in the works, and they built it in this way, right? That the part of the hardware and software that controls the suit functions is separate from kind of the communication system and the informatics system, so that can be quickly updated and iterated without having to recertify the flight software, right? Because if you keep them separate, then you can develop them in a separate fashion. So. These things like AI assistance and whatever, eye tracking, and I most definitely expect those things to be incorporated into those new suits over time. When it comes to kind of, robotic assistance, right? So exoskeletons or some sort of mechanisms that are incorporated into the spacesuit. My understanding that in the past that wasn't done because it does add bulk to the suits. Right. And if your suit gets bigger, that means your airlock hatch has to get bigger and all these things. Right. So it kind of it entails some other changes to your vehicle architecture. But,
With
Right now,
3D
the
printing
plans,
and stuff like that, now we can.
yeah, exactly. You can build stuff on the moon, right? And the idea when you look into ISRU is not just to get water and oxygen from the lunar surface, but also build stuff, right? There's it's made, the lunar regolith has lots of aluminum and titanium in it that you can, if you have the,
And we have a lot of advancements in material science, alloys, which is like ridiculous how much structural integrity we're getting through very thin diameters or thicknesses
right,
of material.
And so that having mechanisms in the spacesuit that help you move around in that inflated balloon, that of course would be wonderful. And so I'm not aware of any kind of active development being done, at least by NASA or any of the direct industry partners. I'm sure there's a startup out there doing exactly that. But yeah, I mean, that's definitely one thing that would be helpful.
Okay, so let's now shift gears to the virtual suit and the Thermos. You've developed the vSuit and the Thermos platforms to create an integrated simulation of an astronaut's walking on the moon, like the moon's permanently shaded regions. Those platforms model everything from the heat radiation of a crater's wall to the astronaut's own metabolic output if you're doing high-fidelity models. Does your vSuit follow the same architecture philosophy as your VHAB? And
yes.
Yeah, and can you share an example of it?
Oh, and the thing is, so the spacesuit up until basically the outer layer of the suit, that's basically VHAB. It's a model in VHAB. And then the Thermos, which was initially developed by another colleague of mine in Munich, the kind of my starting point there was that the thermal simulation stopped at the outer layer of the spacesuit, right? So it just said this, because it's a computer graphics type modeling. And so it's the geometry is made of triangles. And basically my starting point was, here's a triangle on the spacesuit that receives, 400 watts per square meter of thermal energy. And that's all the information that was provided or is provided by Thermos. And then I basically could develop the interface between the two to basically communicate the current temperature to Thermos to do the thermal simulation, and then communicate the thermal energy balance, basically plus or minus X watts per square meter to the VHAB model, which then, has a thermal model of the spacesuit in it with the, different layers of the spacesuit and everything to calculate all the other temperature effects.
So why is it to the outer layer? Because why don't you take, let's say, 1 meter space outside of the suit? Because let's say micrometeorites, upon impact, they also create thermal heating and protection. And how does the meteorite protection system interact, isolating the radiation protection from thermal protection?
So spacesuits in general don't necessarily have a dedicated radiation protection system. It's one of the issues that's kind of counter to me thinking EVAs are cool and we should do more of them, because the safety community actually says, no, we should do as few EVAs as possible, because amongst other things, you have a higher radiation exposure when you're outside rather than on the inside of the space station or spacecraft for that matter. Micrometeorites is something that I don't cover at all. So it's, if you get hit, if it's small enough, then, you can, the leak will be small enough that your reserve oxygen will let you get back to your habitat. And if it's too big, then unfortunately you're dead fairly fast. And there's not a lot of area in between.
Okay.
Right? So yeah, that's something I don't really consider. In terms of the modeling, the Thermos, as the name implies, it's a thermal simulation, right? So the only thing that was of interest in the development of that tool was the thermals. And kind of similar to the VHAB being a dynamic life support system simulation rather than a static life support system simulation, Thermos is a dynamic thermal simulation tool rather than a static one, right? Because for most of the other thermal analysis tools that are available, they do steady state calculations because those match kind of what you do in thermal testing of spacecraft on the ground, right? You go to a kind of a worst hot case, and then you just stay there and see what the equilibrium temperatures are. And then you do a worst cold case, do the same thing. And then that's kind of what you use to validate your models with. And for spacecraft that are in Earth orbit or in geostationary orbit or somewhere in deep space, right? That's fine because they have a defined position. The position of the sun, changes relatively slow, right? So you have kind of a certain set of thermal conditions that you're in.
Mm-hmm.
But when you're looking at moving objects on the lunar surface, right? So not just spacesuits, but also rovers,
Mm-hmm.
you can go from sunlight to shadow back to sunlight in a matter of seconds.
Mm-hmm.
So the thermal dynamics are
The differential, yeah.
way higher than they are than when you're in orbit. And that was kind of the starting point for the development of thermos, to have this kind of dynamic system, with the idea that if you do a dynamic thermal analysis, then your operational envelope is actually smaller than your worst case hot, worst case cold situation. But it's smaller, right? Because you don't do that, right? You don't go into a permanently shadowed crater and stay there forever until all of your temperatures don't change anymore, right? You don't do that.
Okay.
Yeah. So, and then that's why only it was only considered into the outer surface of the spacesuit.
Is the Thermos platform can be integrated into the vSuit as a model?
Yes, I mean that's basically what vSuit is. So vSuit integrates Thermos with a VHAB spacesuit model and kind of links the two together. Makes them talk. Yeah.
Gotcha. Okay, so a key piece of your research is redefining walkback limits. Can you share with our audience what a walkback limit is and why is it important?
Right. So it's something that goes back to Apollo, right? So for Apollos 15, 16, and 17, the astronauts had the lunar roving vehicle, or the rover, at their disposal. And so it's an unpressurized rover. So they were wearing their spacesuits and were kind of, it looks a little bit like a dune buggy. And they could use that to traverse fairly far away from their lunar module. The thing is, though, everyone wants to minimize risk, right? As we've mentioned a couple of times. And of course, if you have a car, there's a risk that your car breaks down. And so as a result, there was a rule, so-called a flight rule. There's for every human space mission, there's hundreds and hundreds of rules that govern how the mission is operated. And there was a flight rule that the astronauts were not allowed to distance themselves farther away from the lunar module, right, which was their lander and their safe haven, than they could walk back with just their suits. And so they did some simulations on the ground to try and calculate, kind of based on the individual crew member, right, what their metabolic rate was when they were walking at certain speeds on a treadmill, to see how much oxygen and cooling fluid they would consume. And then from that, they calculated kind of how far away from the lunar module they were allowed to be, dependent on how much stuff was in their backpack. Okay. Right? So at the beginning of your EVA, all your consumables are full, right? Your water tank and your batteries and your oxygen tank. So at the beginning of your EVA, you can go really far away. But the more you consume your consumables, the further or the closer you have to come back to your spacecraft. So what they did is they got out, they set everything up, and then they drove away as fast and as far as they wanted to, and then worked their way back towards the lunar module. For the different EVA traverses. But that walkback limit, that's actually, fairly complicated to calculate, because it depends on where they are, how far away they are, and how much stuff is in their backpack. And doing that required they had some transparencies that they put on top of the handwritten plots of the consumables levels. It was the 60s and early 70s. So the assumption that I made was, well, we're going to have this really awesome model of a spacesuit that I made in conjunction with a lot better knowledge of where the astronauts actually are and what the terrain looks like, right? Because now we have, fairly high resolution digital elevation maps of the lunar surface. Hopefully we'll have a very good idea of exactly where the crew is at any given point, because we'll have better personal navigation systems that can track kind of where they are on the map, and then kind of putting the two together to calculate the walkback limit better, and also calculate a better route home. right? Because back then, the idea was that they would just follow the rover tracks they came out with back home to the lunar module. And if you're, walking, you can maybe go somewhere where the rover can't, or you can take a more direct route because maybe you didn't go in a straight line to where you wanted to be first, but you did a little winding detour. Yeah. And so I did some simulations with that and kind of recreated an EVA from Apollo 15. And I don't know results off the top of my head because it's been a couple of years, but there was a significant difference between the walkback limit that they actually had and the walkback limit that they could have had if, they had known better where they were and the better consumables estimation.
Yeah, I hope also they're calculating the tripping and the ballerina dancing they're doing also, because that takes a lot of energy.
I was being generous. Also, I think, the Apollo suits, they were basically all soft elements, right? So, there were some, metal adapter rings between the wrists and at the neck, but the rest of the suit was actually all soft goods. And so those are, you have to take even more effort or put more effort into making that flexible and movable. And they did some, for the shoulders and the elbows and the knees, but not so much for the hip. That's actually one of the big improvements in the new suit design. That they have a more rigid, I think, waist hip brief is the technical term for the component, with some bearings at the hips that make especially the lower body way more mobile. Than the Apollo suit, right? And one of the reasons why they were kind of, bouncing and jumping up and down was that they were using the kind of flex and spring force of the spacesuit to move around rather than just their own locomotion apparatus. And that's going to be different with the new spacesuit.
So what would it take to extend those limits, those walkback limits for next generation planetary EVAs?
Well, in short, it's just a function of the consumables, right? So if you're looking at an unpressurized rover, which is the new version, is called the LTV, the Lunar Terrain Vehicle that NASA is developing, again, with two commercial entities providing competing designs, is that, if you have more reserves in your backpack, right? More oxygen, more battery power, more coolant, water in the current design, and more reserve oxygen, right? There's always kind of a secondary or emergency oxygen system in there. The more you have of that, the more you can walk back.
Okay.
At some point, though, if fatigue becomes an issue, right? NASA in the early aughts, I think, did what they called a 10-kilometer walkback test, where they had people in pressurized spacesuits on treadmills walking 10 kilometers.
Wow.
And I think that's kind of somewhere near the upper limit of what you can physically accomplish in a certain amount of time and without becoming too tired. I'm sure if you're actually on the moon and you're in an emergency situation, that sets free some reserves that you can't access unless you're actually in that situation. Yeah. You also need to take into account, right, that maybe there's an injured crew member that might not be as mobile as an uninjured one, or you need to carry transport the other person on some sort of stretcher back home. So lots of things to take into account. NASA actually only kind of took into account a single failure. So it was either the rover fails or one of the suit fails, but they didn't account for the case that the rover and one of the suit fails.
Wow.
So if that had happened, then at least one of the astronauts would have died.
Okay, knock on wood. Claas, a common thread through all your work is in both the life support system and spacesuit is the deep integration of the human. This brings us to the crucial topic of human factors. For many engineers, the human is an inconveniently variable boundary condition. How do you define human factors in the context of your work?
Yeah, I guess, the inconvenient is, of course, true, right? But, that's as I've said before, right? The human is at the heart of the life support system, right? It's the whole reason why that spacecraft subsystem exists in the first place. We need to deal with them. I think that's, for me, part of the fun of the challenge of developing life support systems, that it's, same flow rate all day, every day. And on top of, the individual human being variable, there's also variability between humans, right? So large people and small people, people and, heavy people and light people. And there's differences between different genders and all that stuff. So it's you need to make sure that everybody can go that wants to go. So it's part of fun.
So is it about designing for the limits of the human performance, or is it about also designing systems that can augment and expand those limits?
Definitely both. I mean, for the spacesuits, right, what we talked about, right, the kind of robotic exoskeleton assistance, that's not as much of a focus right now, but I'm sure it will be in the future.
Mm-hmm.
For life support systems, it's all about making sure that you can accommodate all crew members' preferences and individualities. For spacesuits, as we said, human-shaped spacesuits, that's very at the forefront, right? Making sure that you have a suit that actually fits the people. You're in there, with preparation and tear down for 10, 11, 12 hours a day. So that's a long time. And if you've ever worn, a shirt that doesn't fit you, or shoes that are just a little bit too tight, that's uncomfortable, right? And that's not something you want to happen to you on the moon or on Mars when there's no, shoe store available in the near vicinity, right? And so there's lots of effort being put into making the suits flexible in terms of sizing, right? So you can have different lengths of arms, different lengths of legs. The upper torso is a hard component, right? So it's a single piece of metal where the rest of the components attach to, right? So they have different sizes of the upper torso, and also for the waist hip brief, to make sure that we can accommodate a wide range of occupants.
So is there a specific type of human system interaction problem that is uniquely suited to be solved by simulations, and one that can only be solved by putting real people in a physical analog?
Yeah, I mean, I think so, and it kind of is going to the same direction with what we talked about earlier about AI and then generating the training data, right? So with simulations, you can do things that humans can't, right? So I was an observer for some of the human in the loop testing that was done at NASA for the spacesuits, right? And they usually run these kind of fairly realistic metabolic profiles when they're doing uncrewed testing, right? Okay. But that's, step changes, right? Okay, now we're at this metabolic rate, now we're at this metabolic rate. And having the human in there, right? It's, all the lines are nice and straight. They're all squiggly and curvy. But then again, right, when you're really trying to stress the system or trying to find kind of the boundaries of what the system can do, right? You always design to a certain set of requirements, but then finding out the actual hard capability of the system is that sometimes hard to do with humans, right? Because you can't, bake them at 45 degrees for hours on end, or have them do, 1,200 watts on the treadmill for 10 hours, right? That you can't do that because the human will break. So those things, I think, are very, very well suited to be addressed via simulations, because we can just do things that human bodies can't do. And then on the other hand, specifically these very minute things when it comes to the interactions between the human body and the suit, right? Getting the feedback from an actual person that's actually in the suit that can say, there is, this little tiny thing that's on my back, on my right shoulder, that's, kind of poking me whenever I do this movement. I don't think we'll ever have computer models that are that good, that can provide that type of direct human feedback. So yeah, as always, there's room for everyone, and we need everything.
Claas, we started this conversation by talking about the need for a cross-disciplinary, holistic view. Your work consistently returns to this theme, analyzing the entire system, the crew, hardware, environment, and mission, as one interconnected entity. To bring it full circle, what is the most significant benefit of this holistic system-level approach?
Well, I mean, most of the things that I do are in support of the design of spacecraft with humans in them, right? We're being modest here, right? Or not modest, or realistic is the right word. A university is not going to build a human spacecraft. That's unless someone wins the lottery here from my team, we're not going to do that. So what we're doing is we're trying to help. Right? We're trying to help designers of the actual systems make good decisions and confident decisions that ultimately ensure that we can do the human space exploration missions that we all want to see safely and hopefully in cost-effective manner for everyone involved. And I think to do that, it is absolutely necessary to make sure to cover all aspects of these systems, and especially the interactions, right? That's kind of my mantra, right? You can't draw your system boundary, your little dots around one little part of your system and say, hey, it works for me, right? That's bad. You don't want that to happen.
Okay.
You always need to make sure that it works as a team with all the other parts of the puzzle.
Okay, so we've touched on many emerging technologies today: AI, digital twins, advanced material, virtual models. Looking beyond your own specific research, what is the one emerging technology from a different field that you believe will be the most disruptive to human spaceflight in the coming decades?
That's a big question. So, emerging technology. It's kind of hard to see beyond the kind of immediate AI, explosion that's happening at the moment. I mean, I'm sure there's, the work that I do is, very much on the kind of system level of engineering, right? So systems engineering. So and I think that's probably true of lots of aerospace by training, I'm a mechanical engineer. There's fundamental science that's being done, right? In physics and chemistry and biology or material science. That produces new results and new concepts every day. And I think what we do as aerospace engineers is we find those new concepts, and then we have the insight of where those technologies could be applicable for our problems, right? Because what I always tell students, right, what's cool about going to space or doing spaceflight technology is everything's extreme.
Okay.
Right, you're going at extreme speeds into extreme environments with extreme temperatures and pressures and all that stuff, and those require creative and extreme solutions that push the boundaries of whatever the technology can do at the moment. Right, so yeah, I'm always on the lookout for things like that.
Okay,
but I'm not the one who comes up with those ideas. Those are my colleagues in the more specialized fields.
So finally, and this could be also a question for your self-retreat, if for the next 15 years funding was no issue and you had your choice of collaborators and resources, what is the one big audacious research question you would dedicate yourself to answering?
And I get to dream some more.
Yeah.
Well, I mean, I would definitely love to build my own spacesuit here. And, that's something where we're looking at, double-digit millions of euros to do that kind of thing. So that would be the dream.
Okay.
To have my own spacesuit here. And then, well, if we're really going crazy and money is no option, then I would build a building here where I would have a Mars environment in. So I could, have a thermal chamber with a Martian atmosphere and the Martian temperatures, and where I could walk around with my spacesuit that I've designed for the Martian surface. That would be perfect. And then, we could all do interesting technology development for Martian spacesuits and try and make them as efficient and as light as possible.
Cool. Before we wrap up, is there anything else you'd like to share with our audience, or advice you would like to share, or like plug in something that's happening new coming up?
Yeah, sure. So we're almost at the time here where we're going to do our annual space station design workshop. So it's more geared towards students and young professionals, but hopefully there's lots of those in the audience. And so it's a 1 week workshop where 2 teams of about 20 students or 20 participants each get to design a space system of sorts. That started off as a space station design workshop, but we've kind of expanded it to being geared towards spacecraft of all kinds. Last year we had a lunar base that the 2 teams developed, and it's very international. So we have people from all around the world that come by, and then they get 1 week or 5 days where it's very intense. They get to build a spacecraft, and then a jury of experts gets to decide which team has the better design. So it's very cool. It's very fun. You can learn in 5 days as much as you can do probably in at least 1, maybe 2 semesters of studying at a university. So I would highly recommend everyone who's interested to apply to that. We also have a sister workshop that's also happening for the first time this year called the Satellite Design Workshop that does basically the same thing for satellites. And so the applications for the 2026 workshops, those will open sometime in the spring. So yeah, be on the lookout for that. And we hope to get lots of cool applications.
Claas, it's been an honor to have you here. Thank you so much for sharing your insights and expertise.
My pleasure. I had a great time.
Me too. To everyone else listening, this is the Omar Al-Laili podcast. Thanks for joining us and keep exploring.